Thank you so much, Jeff, for the kind of introduction. So today I'll be presenting our work on this architecture and co-design framework, which is called the Bishop. My student, Boxun, possibly could do a better job in presenting this work, but unfortunately, he cannot be here today. And with that, so basically, why this doesn't work? Okay, all right. So this work is really kind of being motivated by the fact that transformers are all over the place in today's AI world. And but if you ask this kind of philosophical question, I think the previous kind of presenters have already laid out a very good motivation for this question, right? So where not today's AI is really efficient, right? So, but we can go into quite a bit discussion about this, but on the surface, at least we can see that, today's AI models like GPT-4, they consume quite a bit of power, but still we're facing a lot of challenges, including hallucinations and catastrophic forgetting and so on and so forth. And I can sleep here maybe, okay, all right. And kind of in contrast, we know that brain is fairly efficient. So I'm a person who always feel cold. I need to wear a jacket, but my brain only burns about 20 watts of power, right? And but with this very efficient power kind of dissipation, brain does a lot of amazing things. That's something I think people are still trying to figure out. So I don't claim we have done a complete understanding about brain, but we're trying to kind of take small steps, building systems, mimicking the brain functionality. So with this being said, my team got excited by some of the latest developments in the kind of spiking transformer kind of area, where we are building transformers, but under the carpet we stick in spiking neurons as a compute units. As you know, spiking neurons take spikes activities, spread out over time and can generate spike outputs. So therefore, spiking neurons can encode information using timing, which potentially can be a little bit more efficient. So with that being said, also, the latest kind of training research and kind of architectural level exploration have also improved the performance of spiking networks a little bit, at least. I think kind of the performance gap between ANs and SNs is a little bit kind of shrinking. So this is really a good thing. That's kind of motivated us to really look at the architecture level solution to speed up the inference of spiking transformers. So with that, I think it's still kind of quite relevant to really look into spiking transformers and identify what are the bottlenecks from a compute perspective. We did a little bit of profiling, as you can see here. Majority of compute actually go into the spiking MLPs and spiking attention calculation, and they are also an important contributor to the memory access as well. And with this being said, I'm kind of showing you a little bit of kind of background, right? So, and in recent years, this is certainly not a complete list of the related work, but in the recent years, we have seen kind of spiking hardware accelerators, mostly targeting spiking CNNs. But today we also heard two wonderful talks before this one. But mostly we have been seeing works dealing with homogeneous architectures, dealing with spiking CNNs, but little has actually been done regarding speeding up inference of spiking transformers. That's what we try to do in this work. So kind of the key challenges are to kind of massage our computer architecture design space so that we can efficiently support spatial temporal computation in spiking transformer in terms of computing spike-based embedding, and also very importantly, doing spiking attention calculation. So with this, we kind of identified the three main challenges. The first one is that if you just take an intuitive way of thinking about the spiking computation, you may actually process workloads sequentially in time. You process a whole bunch of workloads at this time point, then you move on to the next. But this will lead to actually a lack of, some sort of a multi-bit weight data reuse, and you had to repeatedly load the same kind of weight data for processing workloads at different time points. Secondly, indeed, biologically inspired networks tend to be super sparse, right? But the sparsity the level of sparsity can vary a lot. So this makes actually exploration of sparsity in hardware inference very challenging. And then lastly, we have a lot of redundancy. So and then regarding to those kind of three challenges, we have three ideas. The first one is that we need to have a new mechanism in terms of packing the spiking data so that we can efficiently process the data on the hardware. Secondly, we may need to actually come up with some sort of heterogeneous architecture to deal with varying degrees of sparsity. And finally, we can explore some sort of co-design strategy where we can do offline or online sparsification and pruning. So correspondingly, in this work, we are kind of demonstrating a few ideas, right? So regarding to the first and the second challenges, first of all, we come up with this concept of token time bundle. This is a way of bundling spatial temporal input activation data so that they can actually be efficiently processed at a given processing unit on our hardware architecture. And secondly, we're going to come up with a combination of dense and sparse token time bundle kind of processing cores for processing dense and versus sparse workloads. And very importantly, we also have a basic design which is basically dealing with some sort of efficient spiking attention calculation. This is reconfigurable. I'm going to go into the details in a minute. And lastly, we have kind of two algorithmic kind of ideas. The first one is to improve the structure level sparsity in terms of token time bundles by doing pre-training. And lastly, during the online kind of inference stage, we can do dynamic error-constrained pruning to improve the efficiency of spiking-based attention calculation. And so with this is kind of a quick picture showing, this is a little bit too busy, but at least, basically what you can see here that is if you start out with just kind of a traditional homogeneous, SN kind of accelerated architecture, you start to bring in kind of the three ideas I have mentioned. At each step, we can actually improve our energy efficiency and the latency quite a bit. But collectively, this becomes actually a fairly holistic kind of approach dealing with spiking transformer models. So with this, let's just kind of go into some of the details. I want to kind of first of all talk about the first idea, which is this data structure token time bundle. To illustrate the points, so here, as you can see on the left, if you just kind of take the conventional time sequential processing of different tokens, sequentially across different time points, you're going to end up with loading the same kind of expensive multi-bit weight data at each time point, which certainly will prevent the multi-bit weight data reuse, degrading your performance. So to deal with this challenge, in this work, basically, we create a bundle which basically packs a number of tokens across a number of time points. Then we're going to actually map each bundle onto maybe a PE on our processing array, so that when we actually process this bundle, we can actually do multi-bit weight data reuse for all the tokens within that bundle. And in addition, as we kind of push our data across our array, we can also share the multi-bit weight data across different PEs. So there are two levels of kind of data sharing. Then kind of move on to the kind of second set of ideas. In this case, basically, as you can see here, this is a highly simplified overview of our accelerator architecture. But if we kind of zoom into that a little bit, essentially, to be able to do very efficient synaptic integration in MLP and the linear layers, we come up with this dense, TTB core, which is basically to process the dense part of the synaptic integration. Obviously here, since we're kind of multiplying effectively multi-bit weights with binary input activations, we don't need to have multipliers. You know, everything can be fully supported by much cheaper select and accumulate operations. I think the previous speakers also kind of commented on this. And you know, similarly, if our input activations are kind of sparse, you know, putting the workload onto a dense core will lead to inefficiency. So therefore, we also incorporate sparse TDP core to handle very efficiently irregular sparse workloads. And finally, you know, if we are done with processing through the two cores, then we had to combine that, right? So we had to kind of do sparse dense addition to kind of complete the synaptic integration for a given layer, and finally we can actually produce binary, you know, spike outputs for that layer. Then the kind of next question is, you know, how do we determine, you know, which portion of the workload would be considered as dense versus sparse? You know, the idea here is pretty simple, right? So here, essentially, we're going to look at our, you know, basically bundles, and shown here, we're going to actually look at, you know, basically we're going to find a set of input dimensions, and for each of them, the number of active, you know, tokens in the corresponding bundles is really small. So therefore, you know, we can actually reshuffle our input dimension, you know, indices, so that, you know, the first part of our workload would correspond to actually the dense part of the synaptic integration. The remaining parts would be the sparse, you know, computation. Then, respectively, we're going to use two different cores to process them. So this is kind of illustration of kind of conceptually how this works. You know, so here, without this kind of stratification into two parts, you know, you have some sort of sparse activities in terms of bundles, but you know, the kind of sparsity level is not perfect for the dense core. It's also not perfect for the sparse core. But if you do the kind of stratification, then we kind of push, you know, them to the two extremes, right? So the upper part over here is, you know, the sparsity level is further intensified, and for the bottom part, actually the density gets, you know, further, you know, intensified. So therefore, they can be respectively processed very efficiently using the sparse and the dense core respectively. So with this, I want to kind of go into kind of the next idea, which is to you know, to compute very efficiently, you know, spike-based attention, which is obviously very critical for any transformer type models. To do this, you know, essentially we have a reconfigurable spiking-based array, and you know, kind of, you know, in a highly simplified manner. So this is kind of the equation we had to kind of compute. You know, this is how we compute basically the attention output, but we kind of split the computation in two steps. And each one will be actually handled by a particular operation modes. In the first mode, we're computing the attention scores, and we try to be smart about that. So basically we understand that even though the query and the key in spiking transformers are binary, but the resulting you know, attention scores are actually multi-bits. So therefore, you know, in the first mode, we make our array architecture you know, score stationary or S-stationary. We can use very efficient and accumulates and operations, again, without requiring any multipliers to do this multiplication very efficiently. Then in the second kind of mode, so we're going to actually finish up the final outputs. Basically, we're going to keep our attention scores, which are computed in the previous modes, in the array. Then we're going to actually flow the value data from the top. Then we can very efficiently compute the final outputs using select accumulate operations. And then we kind of move into a little bit kind of pre-training kind of stage optimization. In this case, the idea is that since we have a heterogeneous architecture which can deal with very flexibly different levels of sparsity, so therefore we want to actually encourage training to produce sparser model. So how do we do that? Essentially, we want to encourage structure level sparsity in terms of bundles. So therefore, we come up with a very simple idea. For each bundle, we're going to count the number of active spikes in that bundle. That gives this z. Then we're going to sum up this z value across all the bundles in our network. And then that becomes part of the training loss. It turns out that if you add this training loss, you can improve the bundle level sparsity, but without actually dropping your model accuracy in any significant manner. So this is basically to show how this so-called structured bundle sparsity aware training works. And essentially by applying this BSA training in the model training stage, we can shift the bundle distribution curve. As you can see here, we have a larger number of input features for which the number of active bundles becomes fairly small. So meaning we have improved bundle level sparsity. And finally, coming to the kind of last idea we have for this work, and we want to further improve the efficiency of computing spike-based attention. And just like any conventional transformer models, we are running into this quadratic complexity with respect to the sequence length, and basically the number of tokens n. When the number of tokens increases essentially very quickly, computing the spike-based attention map gets very complicated. So therefore, this is the place where some sort of pruning kind of can come to rescue us. So the way of doing that is basically, we can actually identify redundant computation in this stage, so that not only we can actually improve the sparsity in this attention calculation stage, but as maybe a side effect, sometimes pruning can also be treated as a denoising kind of process, which may lead to a slight model accuracy improvement, although that is not the primary goal of this pruning technique. So how do we do the pruning? I think pruning is a really common technique across computer architecture or particular computer architectures for AI applications. So if we look at basically this is basically the query tensor. This is the key tensor, right? So if I identify a row where I see lots of activity, meaning the number of active tokens is fairly small, then potentially I can prune out that row. I can maybe reduce the dimensionality of the attention map needs to be computed. But here the question is we need to do the pruning while controlling the amount of approximation error. Turns out that this actually can be done trivially for spike-based computation, because our query queue and the key are both binary. So therefore, for example, if I take out one particular row, which basically has low activity, I know the maximum amount of error induced will be no more than the number of active bundles in that row. So therefore, we can have a pretty simple kind of error control mechanism to prune out a whole bunch of rows in the Q tensor and also the key tensor. Then that will dramatically reduce the size of the effective attention map. So this process is illustrated over here. So basically, by setting up a kind of predefined kind of error bounds, we can actually select a subset of rows whose activity level is below that firing threshold, is below that pruning threshold. We can prune out a whole bunch of rows, basically in the query. Then we can also prune out a whole bunch of rows in the key. Then the corresponding attention map gets reduced dramatically, because a whole bunch of rows and columns, respectively, will be removed from the attention map, which also will lead to reduce the kind of data access to the value tensor, and finally significantly reduce the overall overhead for the attention output. So sometimes kind of the amount of pruning, pruning can be very significant. We can reduce the overall complexity down to something like 2%. So with this, let me kind of go into some sort of a quick discussion of the evaluation. We look at a few different spike-based kind of models, 5 of them. The first 3 are trained using static image data set. Last 2 are a little bit different. So the fourth one is basically trained using dynamic vision sensor based gesture recognition data set. So therefore, there's some sort of spatial temporal information in the inputs. The last one is actually a speech command recognition task. So we kind of synthesize our design using 28 nanometer design kit and standard cell library. So therefore, we can actually evaluate our hardware accelerator. We have a couple of baseline for comparison. So this slide basically kind of tells you what happens in terms of stratification for splitting the total input activation in 2 parts, right? Dense versus sparse. Obviously, since we have a heterogeneous architecture, we want to actually do a good job in terms of balancing the processing between dense and sparse cores, which typically gives you a very good kind of efficiency. But if you just do that, you can actually get a pretty good boost of your EDP, energy delay product compared with this PDB architecture. This is actually quite a good improvement. And as maybe the second kind of illustration here is to consider how possible or how easy it is to choose a suitable size for our bundle. And obviously, this involves some sort of kind of trade-offs as well. For example, if you just look at the effectiveness of the pruning I just talked about, if you have smaller bundles, you tend to actually have a better effectiveness of the pruning. But during the same time, there will be a reduced, inter or inter-bundle key value reuse. So therefore, there's actually a trade-off. Similarly, we're going to actually see a trade-off regarding how efficiently we can process the linear and MLP layers. But luckily, by doing some sort of kind of benchmarking, we realize that no matter what, there's always kind of a wide range of good, bundle sizes you can choose from. They actually give you pretty near optimal results. So therefore, in practice, we can easily choose a decent bundle size that works fairly effectively. So this is kind of to show you how this error-controlled pruning works for improving spiking-based attention. As you can see here, we have 2 models. If you pick a particular pruning threshold, we can actually dramatically prune out our query and key tensors. For example, up to something like 20 or 30 or 40%. As a result, we can actually improve our energy efficiency and latency by quite a bit. But sometimes we even have a side bonus, which is our model accuracy improves a little bit. But this is not always happening. For those 2 models shown here, the amount of pruning is actually dramatic. We can actually prune dramatically. The total amount of computation we need to be done. We need to do actually can be just a few % of the original. So this actually brings up, speeds up the computation quite a bit. So this slide basically gives you the idea of the size and the total energy dissipation of our synthesized accelerator. And not surprisingly, most of the area and the power gets consumed by the 3 major processing cores, dense and sparse TDP bundle core, and also the attention processing array. Other components actually are much less important in terms of the area and the power overhead. And finally, this is kind of showing you a very quick end-to-end evaluation compared with the edge GPU. We have a huge speed up, which is not surprising. Compared with this PTB architecture, we can, on average, achieve close to 6x speed up and more than 6x energy efficient improvements. And our pruning technique, as well as bundle level sparsified wire training also kind of work quite effectively. So with this, I want to basically kind of conclude. We kind of presented a systematic approach and a co-design framework for enabling spiking transformers. We came up with a few ideas. The first idea is to kind of pack our spiking data in a TTB bundle to facilitate data reuse. We also have a heterogeneous kind of architecture. In addition, we have sparsity wire training coupled with error-constrained pruning to further improve the processing efficiency, and we have achieved fairly encouraging results. With this, I want to stop, and I will be happy to take questions.
Thanks a lot. That was very good. Yeah, these are very energy efficient designs, which is pretty cool.